Okay, thank you for having me. I'm going to be talking about some of the work I've done for the first 2 years of my PhD, and this has been done with Friedman and Roger Benson. So first of all, it's just a few people to say thank you to. All of the curators in the museums that I visited to collect my data, the hosts for when I was visiting those museums, my NERC funders, my supervisors, and everyone in the Oxford Paleo group for comments and helpful advice. So modern mammals are an incredibly successful clade. And when we talk about success, evolutionary success, we can actually mean a number of different things. We can mean the longevity of the group and its ability to survive extinctions. We can mean how many species it has or its diversity. Or we can mean how ecomorphologically disparate it is, or its disparity. And mammals really exhibit all three of these traits, but in particular, they're incredibly ecomorphologically disparate. And this is in their jaws and feeding ecology. So we have carnivores and herbivores in their life modes. So we have animals that are completely nocturnal, mammals that can lay eggs, mammals that are secondarily adapted to water, and also in their limbs. So we have mammals that can, we have mammals that can fly, can glide, can climb, can swim, and can burrow. And like I say, they have a really long evolutionary history dating back to the Jurassic, and they actually share the first 2/3 of their evolutionary history with the dinosaurs. But when people talk about ecomorphological disparity in mammals, people are actually working on the KPG boundary and onwards into the Cenozoic. And that's because at this time, the fossil record actually reveals a stark change in the disparity of mammals, and we have what's been termed an adaptive radiation across this boundary. And although we now know that Mesozoic mammals are not as conservative as we once thought, we do have a number of things that are ecomorphologically interesting. So we have things like Rapenamammus up here, who was relatively large for a Mesozoic mammal, and he could eat meat. We have things like Castrocorda, who could swim, and Agilodocodon, who could climb. It's certainly true that they were still much more conservative than mammals that came after. This is particularly noticeable if you look at size. So this is a plot by Alroy, so this is size through time. And you can see, I think it's really clear to see that as you go through time, body mass increases at the KPG boundary. But it's not just in body mass and size that mammals increase their disparity. When Osborn in 1902 actually proposed this idea of adaptive radiation, he also talked about the idea that many of the adaptations that we see in Cenozoic mammals were in the jaws and the limbs of these mammals, so they were changing their feeding and locomotor ecology. And in recent years, people have worked really hard to actually try and quantify this phenotypic diversity, or disparity. So people have looked at geometric morphometrics of teeth and jaws. People have looked at something called patch orientation analysis, which actually looks at how complex teeth are. People have taken continuous character measurements of the jaws and of the teeth and the limbs, and also looked at discrete characters for disparity. And what I really want to do is add to this new wealth of data on disparity through time. And I'm going to be looking at the jaws and the limbs of mammals, but for this talk I'm just going to be focusing on the jaws. And I've taken up to 16 continuous character measurements from the jaws, and I have over 1,400 specimens in my data set, and currently over 800 species. So obviously, due to the nature of the fossil record, it's not possible for me to use all 16 of these traits every time I run an analysis. So for this talk, I'm using the 6 best sampled traits, and they are all of the tooth-row traits and the jaw depth traits. But in future, I'll be running different iterations of this data to make sure that my analyses are robust. So if we first look at disparity through time in size and shape data, I think hopefully the first thing you can all see is that the Mesozoic mammals actually are extremely constrained in their disparity. They have very low disparity. And the second thing you can see is that there is an initial increase across the KPG boundary. But actually, it's not a huge increase. It's actually smaller than we might have expected. And disparity actually increases through time in a stepwise fashion up until the end of our study period, which is the end Eocene. And this is robust for shape data alone, so if we remove size. And also, if we look at sampling, hopefully you can see that actually the peaks in my disparity do not necessarily correlate with the peaks in my sampling, do not necessarily correlate with the peaks in my disparity. So despite having things like Guimarota with its multituberculates and crucifontia, and the amazing Chinese mammals from J-hole, and the meso mammals of the Eocene, which I was actually lucky enough to go and see in hand specimen, they don't seem to be biasing our data massively. And if we look further at this sampling bias, and we look from the Aptian onwards, where I have higher sampling through time, and we use rarefaction, we can see that largely this pattern holds. We have this initial but relatively small increase across the KPG, and then we have this stepwise increase through time. So if we now have a look at my function spaces, what we have here, all of the grey dots here is all of my data through time. And PC1 correlates really well with size. So as you go more negatively to your left, PC1 is getting larger, so animals are getting larger. And PC2 correlates really well with diastemer length. So this is my first shape axis. So starting in the Triassic, obviously I've got a very small number here, so we can't say too much, but things are plotting right in the middle of my PC2 axes. Moving into the Jurassic, things are spreading out a little bit, but basically still in the middle of my data. And these extremities are controlled by things like Cynoconodon and Docodon. The Cretaceous is still quite similar to the Jurassic. So we have, again, a little bit more spread, but basically we're seeing relatively small disparity on the PC2 axes. And here now we have multituberculates, like this really nice jaw of Eubatar, plotting up in the more positive numbers, and we have Rapinammamus with his long tooth row and no diastemer down here at the bottom. And like we saw in my disparity curve, now we can see that the Paleocene, again, we do see this first initial kind of increase in disparity. And this is still controlled in my higher numbers by things like Taeniolabis, these multituberculates, but now we have some pantodonts like Titanoides down here. And once again, the Eocene is where things really start to increase, and this is where all of my data is plotting right in these extremities here. And this is because of things, these large Brontotheridae like Diplodocus. We have Basilosaurus here, and interestingly, although he's quite large, he's actually plotting relatively central on my y-axis, on my shape axes, and that's probably because he's constrained by his aquatic lifestyle. And then down here we have kind of my one anomaly in my data is this Stylinodon. And he has a very squat jaw and peg-like teeth, and he's quite an unusual mammal. So, as I said before, we have this relatively low disparity throughout the Mesozoic, and then once we get into the Paleocene, Eocene, we have our initial radiation or initial increase in disparity, and then we move into the Eocene, which is higher still. So now if we look at all of my data plotted together, so this is all of the time bins we've already seen, and remember that we said that as you move across to the left on my PC1, you're getting small mammals moving to large mammals. I hope you can all see that this is very cone-shaped, this data. And what this basically means is that as things are getting larger, they're able to increase their disparity or their shape disparity on my y-axis. And this got us asking, well, we know that across the KPG boundary, mammals definitely get larger. That's been shown by Alroy in that graph I showed you earlier. So we wondered, are many of the new shapes and the disparity in shape that we see actually locked up in this larger sized animals that we get across the boundary? So what we did was we looked at Mesozoic mammals and then comparatively small Cenozoic mammals, and we looked at their sum of variance. And you can see that actually here, they're relatively small, both of them. So we have 0.05 for the Mesozoic and 0.09 for the Cenozoic. But once we add the larger mammals into the Cenozoic, which we don't have in the Mesozoic, we actually have a sum of variance which is 2 orders of magnitude larger. So it does appear like a lot of this disparity in shape is actually caught up in things that are larger. Moving in, so what we also wanted to look at was that this wasn't just an Eocene trend that we saw as we saw the stepwise increase through time. So we looked just across the boundary as well, so Cretaceous and Paleocene mammals now. And again, we've got low disparity, 0.05 each time. And then we have a 1 order of magnitude increase once we introduce these larger mammals. So, in conclusion, mammal jaw disparity in both shape and size was low during the Mesozoic, and this appears to be despite a lot of new mammal ecomorphologies that have been discovered in China recently. The Paleocene does show an increase in disparity. However, disparity increases again, and possibly even more markedly, into the Eocene. And this is something I really want to look further into throughout my PhD, what might be happening across this boundary and why there might be a stepwise increase through time. Overall disparity has increased through time since the KPG in a stepwise fashion. And also, and possibly most interestingly for my results so far, size does appear to be the dominant control on jaw ecomorphological disparity. So we might actually be seeing a release of constraint in size, which is allowing mammals to spread out in shape function space. So thank you for listening, and if you have any questions.